Okay, let's talk about energy resources. And I'd like to begin with just thinking about where's energy coming from. And we've got solar radiation, we've got geothermal energy, and we've got gravitational energy. That is with respect to the Earth. When you look at the rates of energy flux, 120,000 units, doesn't matter what the units are because it's the relative size compared to geothermal and gravity, which are quite small. Now, the flux, of course, is the rate at which the energy is coming to the Earth. Okay, so when you look at solar energy, it's almost 100%. So it seems like it's a no-brainer. We ought to be using solar energy. Okay. In reality, of course, we use a lot of different types of energy resources, most of which presently are non-renewable, fossil fuels being the dominant. Our renewables are solar, but solar actually is a little misleading, as I'll explain in a moment, when we have wind and we have geothermal. If you look at the energy that we consume in the U.S., and this hasn't changed a whole lot, basically it's fossil fuels. Fossil fuels are over 80% of the energy we use. These little plus numbers are the change from 2011 to 2015. About 10% renewables and a little less than 10% nuclear. Renewables would include biomass, geothermal, solar, and wind. Okay. Now, where's the energy come from? Well, with respect to solar, it comes from incoming solar radiation, where via the process of photosynthesis, we take CO2 and water and we create oxygen and organic material. That glucose, in that glucose is stored solar energy, so that when it's oxidized, the net release is CO2 into the atmosphere, water into the atmosphere, and energy, okay, via oxidation. Now, oxidation could be something as simple as breathing. It could be biological decay, bacterial decay, or it could be burning. All of these are processes by which we take solar energy that is stored via photosynthesis and organic material and is released by oxidation. Okay. Now, in reality, fossil fuels basically have formed as the result of the burial and transformation of organic material. And so quite literally, fossil energy fuels are stored solar energy. What we burn today was basically solar energy that was encapsulated within organic material millions of years ago. Okay. Now, clearly, the rate at which that solar energy is being produced is different than the volume that we have today. And so, like water, when we think about the reservoir size versus the flux, we also have to think about the reservoir size and the flux of fossil fuels as well. Now, we're going to be looking mainly at fossil fuels. That is in part because this is a geoscience course, but also they are the dominant producers and consumers of energy in the U.S. today. But we're going to be looking at other types of solar energy as opposed to stored solar energy via fossil fuels towards the end of, if not today, more likely on Monday. And when we look at these fossil fuels, we have basically two kinds. We've got what we call conventional fossil fuels and unconventional fossil fuels. Coal, oil, natural gas, and in at least their typical occurrences are what we will call conventional. Unconventional also could be oil and natural gas, but in different settings, perhaps in shale. I say tar sands, this really should be oil sands, gas hydrates. These are basically other occurrences in which oil and natural gas occur. And so we're going to see increasingly our ability and our necessity to utilize these unconventional sources. Yes, sir.
What are the characteristics of each type that makes them conventional or unconventional?
I'll get to that.
Okay.
Yeah. Okay, so I'll begin with coal because as you'll notice, there really isn't an unconventional coal. Coal is in a lot of ways the most straightforward in terms of a product of a geologic process. Okay, so if you want to make coal, the first thing you need is a lot of biomass because that's where the stored energy is. But the other thing is you want to preserve that biomass in an an oxygen poor environment, because what you want to prevent it from is being oxidized. And if it's not oxidized, then it's still potentially usable. And then you need to bury it, and you need to concentrate it by compaction. Okay. Now, the place where most coal wannabes are going to grow and still be preserved in a reducing environment would be in a swamp or a marsh. Because with the high water table, that is a reducing environment. So as the high rate of biological productivity results in a higher rate of accumulating biomass, it's accumulating in an oxygen depleted area. So we've got a very thick section of peat, let's say, and peat in fact is burned, not so much now, but it was burned in areas of England and Europe when you didn't have anything else. But if you bury it, at some point it begins to be modified to form first lignite and then bituminous coal and ultimately anthracite coal. And among other things, what we see is the compaction. We go from 50 meters to maybe 5 meters. So there's a tenfold amount of compaction. And in doing so, we're concentrating that stored solar energy. Okay. Now, it turns out how far that transformation has occurred from peat when it was formed to various types of coals depends on the geologic history and the age. So as we look at the geologic distribution of coal fields in the United States, we find that the highest grade coals, the anthracites, are actually metamorphic rocks. And so they are formed only, at least in the United States, they are preserved in areas where you had continental collision between Africa and North America. And so in those areas of high degree of deformation and pressure and heat, along the Appalachians, you have the anthracite coals. Then we have a broader area, and mainly the mid-continent in the Appalachian Plateau, where we have Paleozoic age coal fields. These are basically the great coal fields of Gondwana and Pangaea. They were formed 300 million years ago. They haven't been as highly deformed or metamorphosed, so they're not quite as high a grade, but they're still very high grade coal. Okay. Then we've got large areas in the western part of the United States that are basically subbituminous coals, and those are Cretaceous age, or at least Cenozoic. So Mesozoic rather. Instead of being 300 million years old, they're maybe 120 million years old. And they haven't been buried as deeply, and so they haven't been modified as greatly. And so we're looking at lower grade coals. Okay. So we're looking at lower grade coals in this area here. And then finally, the lowest grade coals are sitting mainly in the Gulf Coast. These are tertiary age coals. They've been least buried for the least amount of time, and so they have the least amount of energy content. There's also some broad areas of lignite coals in areas of the Cretaceous where they've been least buried. Okay. So the geologic history of the organic material, both in terms of their age and depth of burial, determines the grade of the coal and their geographic distribution. Okay. Now, we are blessed with coal. In fact, we have the largest recoverable coal reserves in the world, followed by Russia and China and India. And in reality, much of this goes back to the distribution of those great coal fields prior to the breakup of Pangaea. Okay. And as we'll see, the relative abundance or the size of the reserves is a big driver in terms of what we use. We use a lot of coal. China uses a lot of coal. The Soviets don't use as much, but they've also got a lot of gas and oil. Okay. In fact, we have so much coal that not only are we self-sufficient in coal, but if we continue to use it at the rate at which we're using it, it'll last over 200 years. So we are more than self-sufficient. In fact, we're exporters of coal. That's compared to natural gas and oil, which these figures are wrong and the methodology is suspect, but the relative numbers are important. We've got 10, 15 years if we were to try to use what we have in oil and gas and the rates of productivity. Now, those could be off and probably are off by a factor of 2 or 3, but they differ by an order of magnitude with respect to coal. Okay. Now, coal basically is used for generating electricity. About 92% of all the coal in the U.S. goes to generate electricity. The rest goes for chemical stocks. And it is a significant portion of our total electrical energy source. Now, this particular illustration shows that coal is 40% and natural gas is about 25% of the sources used for electricity. But it turns out that by 2016, that has changed such that natural gas now exceeds the amount of coal used. So we're seeing both a decrease in the consumption of coal and an increase in the consumption of natural gas. And we're going to talk about the geological and technological and economic and environmental reasons for that. Okay. It turns out the relative amount of contribution from hydroelectric and nuclear has stayed about the same. Okay. If you look at coal use from 1948 to 2011, it's been increasing. Now, since then, I should add, it's been decreasing, but I'm using these to illustrate the change in type of coal. We're using less anthracite, even though it's the most energy abundant. That is because it is the most costly to produce and it is the least abundant. We kind of peaked with lignite, and then lignite, again, because of its low energy content, doesn't contribute a lot. Bituminous coal, that's decreasing, but subbituminous has been increasing. And so that has some interesting implications. The other thing is underground coal is pretty much constant, whereas surface coal has been increasing. So what we're doing is we are producing, that increase in coal is the result of surface mining. And lastly, that surface mining of subbituminous coal is west of the Mississippi. Okay. So going back to what I described earlier, that Laramide age or Cretaceous to, let's say Cretaceous age coals in the Cordillera in the central part of the United States, that's basically what's been increasing. Now, it is relatively shallow, which is one of the reasons why it is low grade. So it's being mined by open pit. And one of the implications is it's being mined by open pit in an area that's arid, or at least semi-arid. Remember what we talked about when we talked about the rainfall distribution in the United States. You can draw a north-south line about 100 degrees meridian, and it's semi-arid to arid. So we are doing surface mining of lower grade coals in areas that are relatively water poor. Okay. Now, surface mining means strip mining, and so we basically migrate along an exposed face, and of course in doing so we have a lot of spoils deposits that are left behind. This is a fairly typical strip mine in Wyoming. This area here is basically the front where they're mining, and as they mine it, they leave behind a pile behind them. Now, this is the pile left behind, and this is the pile that was. So what we're looking at is reclaimed land. So that is the intent. We grade it, we revegetate it, and that is, of course, mandated by the Surface Mining Control and Reclamation Act of 1977, and basically try to put it back the way it was. That's not real easy, and of course it requires a lot of water again in terms of getting the vegetation back, etc. It's not quite as hard in Indiana, for example. This is before reclamation and after reclamation. Okay, but what about Texas? Now, Texas, we've got the coals we're using in Texas are lignite. They're tertiary age, low grade. Okay, and they're exposed mainly in an area between here and Dallas. So here's that front face again, where it's mining. Here's those piles of debris. In fact, this is how it works. You basically go through. Here's the coal. You've got a front, and then you leave behind these spoil banks, and you keep working your way until it gets too deep to do it by strip mining, or you run out of coal. Okay, so here's that area of spoils, and that's where they're mining it. Okay, now notice by the time you get to here, it's a different color, and so what's happening is they're bringing in stored sediment and soil to regrade the area. And so the area is being regraded, and in fact doesn't look bad. When you drive past reclaimed areas in that have been strip mined in eastern Texas, East Texas, you don't really know they've been strip mined except that there's no trees. Okay, so it's just grassland. Okay. So we got reclaimed land. Of course, we can do that because, remember, East Texas has a lot of rain. We're much harder pressed to do that in areas like New Mexico, where we have open pit mines, or even like Wyoming, where we have open pit mines. Now, I might point out one thing. This is the reclaimed land. If you look over here, it looks like the poor thing's got measles. These are, in fact, well pads. And so one of the things we're now realizing is that this has nothing to do with the coal, but in fact this is associated with production of tight oil, or tight, yeah, there I think it's tight oil. So this is the development of unconventional resources. And one of the things I would point out is look how closely spaced the wellheads are. This is typical of hydrofracking, where you have to have wells on a much closer spacing than many other settings. So we'll come back to that. There's the active mine, the reclaimed land, and all the well pads. So even though when we're doing hydraulic mining, we're not strip mining, we actually are altering a significant portion of the landscape. Okay. Well, this is a different type of mine. It is a coal mine. It's clearly in a different setting. This is the mountains of Appalachia. And what's hard to see here is this is actually a valley. Now, this is the V shape of the valley, and that valley ends right about here. And then the mountain is a series of flat tops, and there's a little holding pond here. And there's a huge area that's been removed. And in fact, that's what we call mountaintop mining, where you quite literally have a coal and you begin to remove it, or better said, you remove the overburden, dump the overburden in the valley and strip away the coal. And you do that successively until finally you basically have nothing but a big mound of overburden that has both filled the valley and also modified the mountain top. Here's that valley that's been filled. Okay. This is an example of one of those mines before and after as they've been mining. So this is a huge area that's being significantly resculptured by mountaintop removal. And you're looking at an area that's already 1.2 million acres already in West Virginia. So this is a major environmental question related to a type of mining that is not underground mining. Underground mining's got its own problems, not the least of which is it's extremely hazardous for the workers, but also it's very expensive. And so this is a cheaper way of getting coal, but it causes a major change in the landscape and, of course, has major potential for pollution of water supplies. So let's kind of look at the pros and cons of coal for a moment. There's a lot of it, and it's all ours. I mean, that is the main thing, and it's not a trivial issue. But there's other issues that need to be considered as well. The dangers and costs of underground mining is significant. The effects of strip mining, both in terms of the West and also mountaintop mining in the East, is significant. And one of the significances is the both surface and groundwater pollution. Remember the acid mine waste that we talked about with copper. That was because of the oxidation of sulfur, or better said, the oxidation of pyrite, which is an iron sulfide. And so as you leave behind the copper waste, it's oxidized, the waters come through it, and you have H2SO4. Except pyrite's also an accessory mineral of most coals. And so just as those copper mine heaps have a lot of pyrite and therefore acid mine waste, so too do the coal mines. And so there's a major issue in terms of trying to control and prevent water pollution. Arguably the most serious problem is air pollution. First of all, when you burn coal, you emit almost twice the amount of CO2 per energy unit as you do burning natural gas. So first of all, we're doubling the amount of CO2 for whatever benefit we get. It also has high SO2 because of that sulfur, that pyrite and other things. Methane is a major issue, the fly ash that comes up, and mercury. There's a lot of mercury that's emitted from the burning of coal. So let's look at the production stage for a moment as we leave the mine. Oh, and by the way, we have to get that coal from the mine to the power plant. And so I may have mentioned earlier that in spite of the fact that we've got coal, lignite, less than 200 miles away, we don't ship that to the Richmond-Rosenberg power plant. They get their mine from Wyoming, 1,600 miles away. And so we have these long coal trains that are coming. And it seems kind of strange that we would do that, except that it's such low-grade coal that even sub-bituminous is cheaper to ship it 8 times as far. So what do we do with that low-grade lignite? We actually produce it on site. So we burn it on site, we generate electricity, the plants are there quite literally next to the mine, and then you just transport it by wire. So we call that coal by wire. Okay. Now, those coal plants, those are what this is generating capacity as of December 2016 versus age of the power plant. That's kind of an interesting story we see because the oldest plants, the oldest power sources that we're still getting power from are hydroelectric. That makes sense because Hoover Dam is still producing hydroelectric power. A lot of the other early power plants have been disabled. Then we began to get, after the Korean War, we began to get more coal-fired plants. Hydroelectric still pretty good, but now we're beginning to get natural gas coming in. So natural gas is coming in. Coal production peaked in about 73. Or better said, coal production for power plants peaked in about 73. And the reason for that peak was that we're beginning to get more and more both natural gas, and now we're getting nuclear coming in as well. So nuclear pops in about 1970, and we're getting some others as we get over to here. Notice the green is popping up. These are our renewables, including wind and solar. So we're generating a lot of new power. Most recently is natural gas, wind, and solar. We haven't really had any significant new coal-fired plants since about 85. And we've had no new nuclear plants. Okay, so we've seen a change in the both frequency of building power plants, but also the type of power plants being built. Okay, so if we look at how that plays out in terms of the main energy sources for consumption, well, we got petroleum up there, although petroleum's kind of an odd one to put here because we don't use petroleum very much for generating electricity. Natural gas and coal are used almost exclusively for electricity. And so we're seeing that there's been a decrease of use of coal coincident with an increase in the use of natural gas. And if you translate that, this is in terms of British thermal units, this is in terms of the CO2 that we're getting. Now, there's been an increase in CO2 emitted from natural gas because we're using more natural gas. Okay. There's been a significant decrease in CO2 from not using coal. And what we're seeing is the rate of increase is much less than the rate of decrease. Remember that 2-to-1 factor. Okay. So we're seeing significant drops in the CO2 emissions associated with the burning of fossil fuels, but it's because of the replacement of coal for natural gas. Okay. Now here are those coal plants. Again, you notice bituminous. This is the Paleozoic sources. We've got subbituminous. That's mainly the Cretaceous sources. We have these little lignites here. Now notice we got subbituminous plants down here. Those are coming from way up there in Wyoming. Okay. So we look at coal production, decreasing rapidly in the Appalachians, pretty consistent in the interior, decreasing in the west. Okay. Now, part of that and this shift to natural gas is associated with cost. The price of natural gas has been fluctuating, but if you think of the price per kilowatt hours, okay, coal, if you look here, you'll see that natural gas was more expensive and now it's less expensive. Well, now it's beginning to get more expensive. So we're just about at a cutover point. And you're going to see for a while that it may be more expensive to produce a megawatt of energy, electricity, from natural gas than coal. But that's predicted to change soon. Okay. So one of the problems that we have is what kind of predictions are we going to make? What are these predictions based on? And what implications does that have in terms of both the production and availability of fossil fuels, but also economic and environmental questions? The shift to natural gas has been largely driven, or better said, initially driven, by the decrease in cost. Okay. But it's also driven for environmental reasons. We'll talk more about that in just a moment. Okay. you worry about air pollution, you need to worry about power plants. They are the classic point source pollutant for air. Half the mercury in the air, 3/4 of the acid gases, think acid rain, almost 2/3 of the SO2, etc., are coming from power plants. Okay. Now, with mercury, we've already said that the amount of mercury consumed industrially has been dropping because we know the health hazards associated with mercury. But we're still putting a lot of mercury out in the environment. And where's it coming from? It's coming from those power plants. So, let's see. It used to be, I say way back in 1990, that if you looked at power plants, municipal waste, and medical waste, that they were more or less sub-equal contributors to mercury pollution. But by 2005, municipal film had a 96% decrease. That, by the way, had to do with burning waste. Okay. And a 98% decrease in medical waste. Again, mainly burning. Okay. So there's been tremendous decreases in the amount of waste, or the amount of mercury, and that's what this is in part related to, until you get to power plants, and there's been a 10% reduction at the same period of time. So we really haven't done a lot to reduce the amount of mercury that we're putting into the air from power plants. Well, that was until a couple of years ago with MATS. Now, I had a I had a definition of it later. MATS basically is a legislation tied to the Clean Air Act that is mercury and other atmospheric toxins. And what it does, it establishes power plant emission standards. And it only applies to coal and oil-fired power plants with capacities over 25 megawatts. Okay. Now, what it does, it results in 90% reduction of mercury, 88% reduction in the acid gas, and 41% reduction in SO2. So this is a major piece of I won't say legislation because it's tied to the EPA's mandate to essentially enforce the Clean Air Act. Okay. Now, what is driving that? Basically health risk. Okay. And so this is arguably, or one estimate better said, for just the health benefits of the implementation of MATS. Okay, this mercury and atmospheric toxins. Okay. What is that worth in dollars? Well, that's kind of hard to say, but EPA says maybe almost $40 to $90 billion a year, and depending on how much you have to pay to implement MATS, it's like $1 gets $3 to $9 in benefits. This is the cost-benefit ratio that we always are looking for. The problem is trying to estimate how much it's going to cost to implement MATS and what is the benefit. And not only what is the benefit, but what is the dollar equivalent. Ironically, these are days missed. That's probably the easiest thing to figure out. But, you know, how much is premature death worth? This is part of the problems of trying to do a cost-benefit analysis with these environmental issues. Okay. Well, MATS came about just before the Clean Power Plan was implemented. Now, MATS has been approved by the Supreme Court. It's now a law of the land. The Clean Power Plan is actually on hold. Okay. But they are related in the sense that the Clean Power Plan is a plan to try to reduce CO2 even more than would be reduced by MATS alone. Okay. And Basically, you want to increase heat efficiency and reduce air pollution of existing plants. You want to increase the use of natural gas plants, and you want to increase the use of renewable energy sources. So that's more or less the plan, okay, that's on hold, okay. Now it turns out, though, that the energy companies have already been trying to implement MATS, okay. So from December of 2014 to April of 2016, really less than a year and a half, you've had a huge number of upgrades of the facility. These are the generating facilities which have not changed. These are the facilities that have added additional pollution controls as required by MATS. And these are the ones in gray that have been taken out of commission. And these right here switch to natural gas. So you're seeing all of the possible responses already starting, okay? And for the most part, most of it has to do with carbon injection, activated carbon injection, absorption systems, scrubbers, etc. So these are various techniques that are being implemented in order to meet the higher standards, okay? Now, this is what I meant to have earlier, and that is that the mercury and air toxin standards, or MATS, is basically expected to cause about 40 gigawatts of coal retirement by 2020. Well, they've already had about 20 of those by December 16, okay? So here's that reduction in the percent power by coal. But you don't have to necessarily abandon coal. One possibility is CO2 carbon sequestration, CCS. Now what that is a plan to take that CO2 and shove it into the ground. Now, it requires, or at least a large portion of this system, requires gasification from burning coal, or from coal. And so that generates what's called a syngas, or a synthetic gas, from coal. Now, if you look at on the right, this is what you get if you burn coal. This is what you get if you burn the syngas. And so you're seeing up to a 60% reduction in CO2, 25% in hydrogen, 4% in nitrogen, etc. Okay. So this is a much cleaner burning fuel. And in fact, what you can do, and I'm not going to tell you the story because you can't really read it too much. Ideally, in this particular example is what's going on right now in the Parrish plant south of Richmond. It's the largest plant that's trying to use carbon sequestration and recycling in the country. Now, it's a test plant in the sense that the government put in maybe $190 million, the federal government, to see if this would work. And it's working pretty good. And it just came online literally a few weeks ago. But you take this waste, and conceptually it could be any of these organic materials, but in this case it's coal, and you basically gasify it. And that produces solids, which you can sell, and then gas, which comes off, and now you've got a gas, and you're going to begin to strip it of various components. You're going to take out particulates. You're going to take out the the sulfur in SO2 to generate sulfuric acid. You can sell that. Then you're going to continue, you're going to strip off the hydrogen, and you can use that for a fuel cell. And then you're going to strip off the CO2. And that basically can be used for both fuels and chemicals. Now, in this particular example, though, it's a little more complicated because that CO2 is then brought back and burned to generate electricity. And in addition, this heat, the excess heat, is also recovered to have electricity as well. So you have a combined cycle where you're using heat generated from the gasification plus burning of the CO2 that you get to generate electricity and CO2 for sequestration. So it's a complicated story, and you can't really read it well, but you need to think about this flow, this workflow. Now, in the case of the power plant, the Parrish power plant, that carbon, or better said, that CO2, is being piped a couple of 100 miles to a oligocene oil field for secondary recovery. And so they're injecting the CO2 in to squeeze out more water, and squeeze out more oil. And so we are significantly enhancing the oil recovery by injecting the CO2, which then stays in the ground where we leave it or sequester it. So this is arguably one of the better pieces of news with respect to trying to have, quote, clean coal. Okay. Now, having said that, it costs a lot of money. And the technology for pumping CO2 back into the ground is still an issue. And so this is kind of the leading edge of using technology to try to satisfy increasingly strict emission controls mainly because of environmental constraints. Okay. Going back to the Clean Power Act, the goal was to reduce nitrous oxides, SO2s, and carbon. It's on hold. But if we had it, then the projection is that this is what coal production through 2040 would be. If we don't have it, it's going to be up here. So we know that if we don't implement the Clean Power Act, we're going to see a significant difference in, among other things, air quality. Okay, and this is the CO2 emissions, the difference in the amount of CO2 that would be produced if we don't implement the Clean Power Plan. Now notice though, it says reference case. Oh, and one other thing, it's not just power plants. If you look at total energy, way up here. So when we talk about the Clean Power Plan, we're only talking, or when we talk about MATS, we're only talking about power plant emissions. This is everything. And what that is mainly is cars and industry that's not generating electricity, but using energy. Okay. So power plants are our dominant point source of air pollution, but they're certainly not the only one. Non-point sources and other industry point sources are really important. Now, let's go back to this question here. Reference case. When we start predicting anything past tomorrow, we have to make a lot of assumptions. And so those assumptions need to be clear. You've already gone through that thought process with the assignment you turned in. You're trying to predict where the riverbank is going to be in 60 years. You had to make a series of assumptions. Okay? You were trying to predict what the flood frequency would be for some time in the future, 100-year flood. You had to make that using stream gauge data, but again, using assumptions. Okay, what does this mean? Well, the reference case for the Department of Energy basically assumes the current laws and regulations haven't changed throughout the projected period. That's 2040, some cases 2050. It also doesn't look at proposed legislation. Okay, so it just says we're going with the status quo. This is the status quo. We're going to assume nothing's going to be terminated. We're going to assume nothing's going to be added. Okay, and we're also going to have to make some assumptions about things like the price of oil and the GDP. The GDP, because that's going to govern consumption. Okay. So there are actually alternate cases besides the reference. For example, there's a high oil price case, a low oil price case. So if you want to guess what the price of oil is going to be in 2040, they guessed $109 for their reference. They've got another prediction based on $43 and another prediction on $226. Okay. If you want to guess what the growth rate of the American economy is, their guess was 2.2, unless it was 2.6 or 1.6, in which case these are additional models. And there's yet another series of things based on technological changes. Do we have a lot of technological advances or nothing more than general? So the reference case is what you will see in most cases. But as I'll show later, there's a tremendous disparity in terms of the predictions, depending on these multiple choices. Yes, ma'am.
Is the reference case something like the mean, like of all the research you've done and all the predictions?
No, that is another way that the USGS will sometimes predict reserves. They'll look at statistical distribution between them. But now these are really just different models. Okay. Well, we're still trying to make predictions. This is actually from British Petroleum. But one of the predictions is that it's not just the U.S. or even groups of more developed countries like Europe and the U.S. and Canada. This is China. And look what China has been doing with respect to coal up until 2015. They almost single-handedly have boosted the amount of coal and therefore CO2 into the atmosphere. Okay. Now the good news is they're projected to level off. Is now coming in. And remember what I said about where the reserves are. It's the U.S., Russia, China, and India. Okay. Now, India doesn't really want to use this much coal. I'm sorry, China. Because the air pollution problems in India are unbelievable. Again, China. Think of what I mean, not what I say. So we've seen a tremendous increase in hydroelectric. That was the Three Gorge Dam. We've seen significant and continuing decreases in coal because they can't afford the environmental cost of coal. Okay. We're a little slower to pick that up, but then our air quality is not nearly as bad as theirs. Okay. Again, worldwide, we've seen gas continuing, coal decreasing, and there's an interesting place here. Now these dashed lines are basically other models where you're going to see globally natural gas taking over coal. Okay. Now we're going to see that sooner in the U.S., and that's one of the things we're going to look at. Okay. Okay. So let's look at petroleum and natural gas. And in particular, what is the difference between these different types of fossil fuels? Hydrocarbons are basically organic rich compounds of carbon and hydrogen. So we're looking, these are our coals and our natural gas and our petroleum and petroleum is a liquid hydrocarbon. Okay. So we're going to focus initially on petroleum. We'll often use the term oil. As we'll find out, there's a whole gradation from very fluid, low viscosity oil to sticky, viscous tar. At some point, we'll maybe even quit calling it oil. But it's all petroleum here. Okay. So what we do is we take an organic rich source rock, we maturate it, and magically we get oil. Maybe not magic, but that's basically what we're doing. So it starts with that high amount of biomass in the source material. Now it turns out the type of biomass is important to determine whether or not we're going to generate oil or gas. If the biomass is predominantly algae, that's a hydrogen-rich biomass that tends to give us oil. If the biomass is largely wood, and you can think terrestrial source, is typically hydrogen poor, and we'll get gas. Okay. Now, gas and oil can occur together, in which case we call it associated gas, or you can have gas without oil, and that's non-associated gas. Okay. So recognize that as we begin to maturate these source rocks, you're going to have a mixture of sources, and you may well have a mixture of gas and oil associated with each other. So we know what it takes to form coal. What about oil and gas? Well, you start the same way. You produce a large amount of biomass, but in this case, either algae or wood or both. And when we think of algae, we think more marine algae. So think more of a marine organic source, whereas with the wood, think more of a terrestrial source of organics. Okay. We still need to preserve it in a reducing environment because, again, if it's oxidized, it loses its energy. Okay. We need to bury it like coal, and with heat and pressure and time, there's maturation. Now, this is kind of where the story begins to split even more. Certainly, the story split initially with the nature of the source organic material, the biomass. We're not looking at a swamp. We're looking at organic material that's brought in and deposited either in a lake or marine environment, preferably in a lake that's stratified where there's no oxygen, or a marine environment where there's low oxygen zones. Okay. But the maturation for coal is just, it's getting more and more compact, the energy content's more dense, but with the maturation, we're actually breaking down the organic matter that is interspersed within the source rock into a liquid and or gas. Okay. So it's in a rock, but to what extent it stays liquid or gas depends on the degree of maturation. And so we have what we call the petroleum window, and that is a zone of temperature from about 50 to 150 degrees Celsius, within which you can generate petroleum. So we need to think of the earth as an oven, and as we bury things, we're heating it up, and we could undercook it, we could overcook it. We're looking for it just right, and that's within that petroleum window. And so the temperature and also the duration determines the type of hydrocarbon. Now, the duration is typically millions of years, which is one of the problems of generating hydrocarbons quickly. Although we can do it synthetically, if we can do it economically, is another story. What happens if you overcook it? Well, you get gas, which isn't necessarily bad. It depends on what you're looking for. So here's the petroleum window, and this is more or less a range of geothermal gradients that occur naturally beneath the earth. If you're in a magmatic rich area like the Cascades, heats up faster. If you're in the middle of the continental craton, it heats up slower. So someplace in here is what sediment buried in organic rich sediment is going to experience. And now notice here it says no oil or gas. That's actually not true. There is early on burial methane that's produced. That is the methane that's generated from waste in a municipal dump. Okay, so it's a biologically generated waste where what you're doing is you've got bacteria that are chewing this up and releasing energy and gas. Okay, but we're not going to be too interested in that. We're concerned with what happens with longer term. And so the first thing we get is kind of a heavy oil, high viscosity. The more it matures, the more it refines. This is almost like a subterranean refinery. It gets lighter oil and some gas. Then we begin to go and the oil begins to break down into mostly gas, and finally there's no liquids left. Okay, so that's the history. And so what we look for as geologists is a source area that has the right history, the right cooking. But that's not all for conventional deposits, because for conventional deposits, they got to migrate out of the source rock to then go into a more permeable reservoir rock. That could be a sandstone or a limestone. Could even be a fractured rock, but usually it's a porous and permeable sandstone or limestone, or carbonate, better said. Okay. Now that migration route can be thousands of vertical feet and tens or hundreds of miles laterally. So there can be a long distance from the source rock to the reservoir rock. And of course, that's, again, one of the big distinctions with coal. Coal is easy. It doesn't take anything to be a coal geologist. You know, it's there. You just have to drill some holes and fill out some forms, because basically it hasn't moved other than tectonically. Okay, but for petroleum, it's a lot harder. Okay. And let's not forget that once it's in the reservoir, you've got to keep it from seeping out. You've got to trap it. So that means that as it's rising through the fluids within this porous and permeable strata, it encounters an overlying impermeable unit. Okay. And that could be, again, a shale or certain limestones or evaporites, etc. Okay. That's a lot of work. Okay. And that's why it's kind of hard to find hydrocarbons. Okay. So here's one of our reservoirs. The blue is just an epoxy we use to preserve the porosity. So blue is porosity, and you can see there's a lot of it. Here, not so good, because it's cemented. So one of the things that's happening is that we are burying both the source rock and the reservoir rock. And so as you bury the source rock, you are cooking the juices. And those juices begin to migrate, and they're looking for a place to go. But that potential reservoir is also being buried, and it's being changed by diagenesis. And so it's being compacted, it's being cemented. We're losing our primary porosity. We may be gaining some secondary porosity. So all the things we talked about with respect to aquifers apply just as well to reservoirs. And so we're trying to tell a very complicated story. We want to try to find that place where the rocks have been matured, where the reservoir still is porous, and then we have to find a trap. So it could be an anticlinal structural trap where basically the oil and gas float to the highest spot they can go, and then they're trapped by that seal. Or it could be a fault where it migrates up and a fault has juxtaposed an impermeable unit. Now faults are kind of tricky because faults can seal it, or they can actually be conduits by which the fluid or gas seeps out. So when you look at gas seeps or when you look at oil seeps, they're usually where the fault did not act as a seal. So not all faults are created equal. And there's also what we call stratigraphic traps, where the nature of the depositional environment in which that reservoir unit was deposited pinches out against a more impermeable environment. So one thing you might imagine is that we've got a barrier island. And in storms, that sand is deposited into Galveston Bay. And we bury both Galveston Bay, in which we've got mud, and these storm deposits, these washover fans, in which we've got sand, and we bury it and wait about about a million years, and we tilt it a little bit. And so now we've got some hydrocarbons coming in. They get into this Galveston Island sand. They start migrating up these washover fans until they stop. They weren't depositing farther. We said we had muds. So that would be a pinch-out type of trap. We can also have diagenesis or unconformities, a variety of things that would trap sediment there. So all of those, both the stratigraphic trap and the structural trap, are ways in which we can trap conventional hydrocarbons. Now, those are actually referred to as discrete type hydrocarbon accumulations. Okay, discrete because they are relatively concentrated in a type of trap. And they're all going to be above the oil window because you've got to have that oil migrate and then be trapped in a particular reservoir. Below here, though, this is where our unconventional oil is formed. And more specifically, where it forms and stays. It's below the, or rather within the oil window, but it hasn't migrated. And so it is distributed throughout or through much of the rock. It is basically the source rock. And so those are the areas that we're going more and more towards looking for. This continuous type of accumulation, these unconventional types. So this is a definition of the discrete type. It's migrated. It's typically bound by water in the down dip area and a seal on the top. And this is bread and butter for oil companies, geologists, and petroleum engineers. This is what we do. We find those things. Okay? Or better said, this is what we did. We found those things. Okay? Increasingly, we're looking for these, where there's hydrocarbon pervasive throughout a whole area. It has not migrated. It may be in sandstone, silt, shale, but the area of extent and degree of heterogeneity isn't known. And so it's just a much more difficult story, a difficult workflow. Okay? So we're going to talk about those shortly. But if we stick to discrete types, which we're most familiar with, this is the story we have, basically, and this is the story for the unconventional accumulations. Okay. Now, for the conventional, these are the basins we're looking at. These are the places where we've had accumulations of sediment, including organic rich source rocks, a burial history that's adequate, and types of reservoir rocks and traps to trap it. And so Texas, as you are aware, has been blessed geologically for hydrocarbon accumulations, discrete types. Of the Gulf of Mexico, the Western Gulf, Fort Worth Basin, Permian Basin, etc. Okay? Then we got the Appalachian Basins up here. Up in here, we're looking at the basins associated with the Mesozoic. Okay? Now, this is where we have the unconventional or continuous hydrocarbons. And again, Texas looks pretty good, a lot of them, Here's the Eagle Ford and the Barrett, and increasingly in the Permian Basin area. There's another area here around Alpine that we'll talk about. And then there's this big area up in the Appalachian Basin, the Marcellus and others. Then we've got that big area in the Williston Basin, the Bakken. So these are all names that you'll read about in the business section or even the front section of the Houston Chronicle, because these are areas that we're exploring today for unconventional hydrocarbon accumulations. Okay. If you had to go to one source to kind of see what's happening, I would suggest you go to the Energy Information Administration's Annual Energy Outlook 2017. I'll post a copy of this for you as a PDF. But this is where you begin to see those projections. And they change every year, which is kind of fun if you take the time of looking and comparing projection one year to another. But here's an example of change. The energy production in 2005, we produced more coal than anything else. Energy production in 2011, we produced more natural gas than anything else. And we consumed more petroleum. So one of the points, there's two things to point out here. Well, actually, maybe three. We produce and consume nuclear at the same rate. We don't import it, we don't export it. But it's remained pretty much constant. Renewables been increasing, but again, we consume all we produce. Coal is reducing or dropping. Natural gas is increasing. Petroleum, well, that's what you see about that. But clearly, we use more petroleum than we produce. Okay. We're doing really quite well with natural gas. But if you look at the rate at which we're consuming things, there's a disconnect between production and consumption. Okay. In fact, if you look at it's clearly in the fossil fuels, and more specifically, it's in oil and natural gas. Because coal, we're actually exporting coal. Okay. So let's take the long view. Let's look at how our rate of consumption has changed for different sources of energy. Okay. Our use of petroleum actually peaked about 10 years ago. But our use of natural gas has been increasing since 1985. Coal just dropped like a rock as natural gas increased, as did renewables. Okay. So, and actually, yeah, let me use this one. It's easier to see. Hydroelectric, constant. Nuclear, constant, slightly decreasing. Liquid biofuels, predicted not to change much. But the changes that are predicted is more or less consistent consumption of petroleum, increased consumption of natural gas, decreased consumption of coal, increased consumption of renewables. Okay. So that is the reference case. That's what we're betting on. Okay. Now we can see how the total amount of energy production, this is consumption, production, we had a little dip, but certainly we've been increasing, but of course the main source of that increase is sitting here in natural gas. Okay. Well, wouldn't it be nice if we could be energy independent? That is to say, if we didn't have to have a net import of energy fuel. Well, we haven't been energy independent since 1958. Ever since then, we have used more than we produced. And so we've had a net, we've had imports that look like this. Notice there are some exports. So net imports is the difference. But these exports are mainly coal. Okay. Now, the question is, what's the future? Actually, it doesn't look too bad. Based on the reference case, the suggestion is that we may start exporting energy sitting here at about 2025. Now again, that's an estimate. It's based on some assumptions. But it certainly is a change from the way it was. So notice this is, if we were to plot this difference, that's what we're plotting here. Okay? So this black line is the reference line. And so someplace around here, we could be energy independent. Except which line do we use? High oil price, that might come even sooner. Low oil price, that may never come. In these two scenarios, the kind of worst case scenarios, we never become independent. Okay, we'll always have a significant amount of import reliance. Okay. Now, where does that independence come from? Well, it turns out it doesn't come from petroleum. Okay? Net independence doesn't mean we don't import anything. It just means we export as much or more than we import. And so what we're looking at is petroleum, natural gas, coal. Electricity, it's a wash. This reference case says we will not be independent with oil, but we will be net exporters of natural gas, and will export more natural gas than petroleum. Okay? And coal will continue to be net exporter there. Okay? So these have some significant implications for us as employees, but also for us as citizens. And the reasons for these changes are important because they are based in part on economics, how much are we going to pay for gas, but in part on how clean is the air we're going to breathe. So these issues are more than just lines. They have to do with our lifestyle and our standard of living. Now, for the longest time, this was an easy lecture for me to give. I kept seeing imports this is just petroleum, getting more and more. And so I used to use this slide. Production of oil has been decreasing since 70. Consumption is largely increasing. We presently import over 50% more than any we've ever used. And I could use that slide until 2008. It really pissed me off because I had to redo my slides. And the reason is that this was okay. Net imports are increasing. Consumption's increasing. Production is decreasing. Just like I told people for 10 years. Except then things started to change. Production started increasing. Consumption started decreasing. Net imports began to drop. Well, that's strange. And this is one assumption, that we're not going to be energy independent. We're still going to import 40%. But how are we going to do it? Well, we're going to have to continue to increase production and not increase consumption a whole lot. Okay. Well, there's a lot of assumptions there. So let's look at this in terms of those models I gave you. Okay. And this is specifically for petroleum. Here's the reference, and actually the reference says we'll continue to import at some amount. But there's a couple of scenarios with high price where we could even be energy independent. But remember what high price was, $230 a barrel in 2040. Now, I don't pretend to know what the price of oil will be in 23 years, but I'll be stunned if it's 200 and whatever. So I suspect the world has changed One of the reasons why I'm not too confident that the high price model is working is this is what the green line is basically real dollars. That is, in this case, for 2003 dollars. Okay, we had hit 122. Gee, that looked pretty good. It was the end of cheap oil, and here was the reference. It was going to increase. The price of oil was going to keep going, and in 2040 it was going to be $160. Okay. Low oil price, oh, that was bad because that gave you all sorts of bad scenarios, except this was the price of oil. Last time I taught the course, I forgot to get it earlier, but if you look at, plot those, we are here. And so we've been pretty much tracking the earlier model for the low price of oil. Now again, that doesn't mean that it won't perk back up to 80 and beyond. But so much of these projections are based on how much oil, what the price of oil is. Okay. I'm going to stop there. Let me remind those of you that came in late that the exam is still the last day of class, but the last day of class has changed. It's now the 1st of May. So the exam is the 1st of May. And I'll send an email out to that